Infinity. It's a concept that has fascinated mathematicians, philosophers, and dreamers for centuries. But did you know that not all infinities are created equal? Some are bigger than others. Today we're diving into the mind-bending world of infinite sets and exploring one of the most profound theorems in mathematics, Cantor's theorem. We start with two types of infinity. The first is the infinity of the natural numbers, denoted by aleph null. This is the smallest infinity. The second is the infinity of the real numbers, denoted by the continuum. As Cantor showed, these two infinities are not the same. The real numbers are uncountably infinite, while the natural numbers are countably infinite. But here's the big question: are there more infinities beyond these two? And is there a largest infinity? The answer lies in Cantor's theorem. Cantor's theorem tells us that for any set A, the power set of A, that is the set of all subsets of A, is strictly larger than A itself. In symbols we write, A is less than PA. This means there's no way to pair every element of A with every subset of A without leaving some subsets out. The proof is both elegant and surprising. Suppose there were a bijection between A and PA. Then we could list every subset of A as Gx, where X is an element of A. But here's the trick. Construct a new set S defined as S equals the set of all X in A such that X is not in Gx. This set S cannot be paired with any element of A because if it were, we'd end up with a contradiction. This shows that no such bijection can exist. Cantor's theorem has a stunning implication. There is no largest infinity. For every infinite set, its power set is even larger. This means there's an infinite hierarchy of infinities, each one bigger than the last. This also means there's no such thing as the set of all sets. If such a set existed, its power set would have to be larger, which is impossible. This paradox shows that some collections are just too big to be sets. Now, here's a fascinating twist. We know that aleph null is the smallest infinity, and the continuum is larger. But is there an infinity between them? This question is known as the continuum hypothesis. In the 20th century, mathematicians Kurt Gödel and Paul Cohen showed that the continuum hypothesis cannot be proven or disproven using the standard axioms of set theory. It's a question that lies beyond the reach of our current mathematical framework. Georg Cantor, the father of set theory, faced immense criticism during his lifetime. His ideas about infinity were so radical that many of his contemporaries rejected them. But today, his work is celebrated as one of the greatest achievements in mathematics. David Hilbert, one of the greatest mathematicians of the 20th century, called Cantor's work the most astonishing product of mathematical thought. And indeed, Cantor's exploration of the infinite has opened up new horizons for mathematics and philosophy. Cantor's theorem reminds us that the universe of mathematics is vast and full of wonders. Infinity is not just a single concept, it's a rich, layered landscape waiting to be explored. So the next time you think about infinity, remember there's always a bigger infinity out there. Keep exploring.